Whenever we factor, we always want to see if there's a greatest common factor in the terms that we're dealing with. So in this polynomial, we have 3 terms. And if we wanted to, we could break them down into their different factors. But I'd like to just take a look at each one of these numbers parts first, and then we'll look at the variables. So the numbers 28, 32, and 40 all have a common number in them. We can factor each one of them by 4. So we can rewrite 28 as 4 times 7, and we'll put that m to the 4th. 32 is 4 times 8, and we'll keep that m cubed. And then 40 is 4 times 10 with that m squared. So you see that each one of those terms could be factored so that it has a common factor. So now we're going to just take that common factor out, and we'll put it in front to show that we can always redistribute it back in to get our original polynomial. Okay, and now we need to look at the variable part. So you should recognize that in the variables, we can split the variables because m to the 4th is just m times m times m times m. Okay, so if that has 4 m's, so this one has 4 m's multiplied together, this has 3 m's multiplied together, then this one has 2 m's multiplied together. So knowing that each one of these terms has an m squared in it, we can factor out the m squared. So like we did before, we have our 4 out front and we have our 7, but our m to the 4th is the same thing as m squared times m squared. And we have our plus 8, and then our m to the 3rd is m squared times m. We keep our negative 10, and our m squared is simply m squared. So now we can see that each one of these terms has an m squared in it, so we're going to factor it out. So we'll include that m squared with our 4 out in the front, and we end up with 7m squared, because we took that one out, plus 8m, because we took that one out, minus 10 because we took that out. We factored it out and stuck it in front. So now you can recall that this is just a distribution process, and we could distribute that 4m squared back in each one of those terms, and we'd end up with the polynomial that we started with. On this particular problem, we have a 16, a 16, and a 14. So we know 2 goes into each one of those numbers because they're all even. But does a 4 go into each number? It does go into the 16s, but not the 14. So it looks like the greatest common factor might indeed just be a 2. So let's just take that 2 out. So 16 divided by 2 is 8 because we're removing the 2. So we're doing basically a division problem by pulling that 2 out. So we have another 8n here and then a 7. And since 7 is prime, there's nothing else that's going to go into those numbers because 7 does not go into 8 or the other 8. Here's another problem, and if you look at that very carefully, you'll notice that 7 goes in each one of those terms. So 49 can be written as 7 times 7n squared. 14 can be written as 7 times 2 times n, plus 7 times 10. So now that we can eliminate each one of these 7s, and we actually don't eliminate it, we just pull it out front. So we take that 7, and of course that's called factoring. We're factoring that 7 out. We end up with 7n squared plus 2n plus 10. Here on this last one, we can see Because each of the numbers are even, we know that a 2 goes into each one of those. But we also need to recognize that the 2 is prime, so that's as far as we're going to be able to factor, because there won't be anything else that can go into the number 2. We also need to notice that each term has the variable a in it. And so since each term has an a in it, we should be able to factor some of those a's away. So when we look at the exponents, we notice that the lowest exponent is the 2. So that means that there are 2 a's in 4, 2 a's in 3, and there's 2 a's in 2. So we can factor out a squared. So I've rewritten that polynomial with all of the factoring done so that we can quickly take a look at what's going on here. So because we have a 2 in each one of these factors, we're going to factor, or excuse me, each one of those terms, we're going to factor that 2 out. And then we'll also notice that in each one of these terms, we have an a squared. And so we'll factor that out as well. So when we take that 2a squared out, we're left with everything that hasn't been underlined. So we're left with a 3a squared plus 2a. Now this term seems to be a little odd because everything's been underlined, but we have one of those in there. So we remember that when we distribute this back, we would multiply by each one of these terms inside the parentheses, and we have to put that 1 there so that we can remember that we still had that 2a squared at the end of that polynomial.